This video introduces the properties of determinants, which will be used to help us calculate determinants using elementary row operations. When we learned about elementary row operations, we used them to put a matrix from its current form into a row echelon form or a reduced row echelon form. And there were three basic operations. We sometimes exchanged rows. Sometimes we took a row and we multiplied it by some constant, or we would replace a row with that same row added by a multiple of some other row. Each of these three operations changes the determinant of the matrix in some way. If rows are exchanged, we'll discover that the determinant changes sign. If we multiply one row by a constant, then the determinant will be multiplied by the same constant. And I wasn't quite completely accurate. One operation doesn't change it at all. If we replace a row by a row plus a multiple of another, that actually does not change the determinant. So if I can do row operations and put a matrix in a row echelon form, I can use these properties to calculate my determinant. In addition to introducing the properties themselves, this presentation talks about the proof that goes into each of those properties. And it's sort of amazing. In linear algebra, almost everything seems to come back to this idea of the dot product. It's amazing, the summation of products. And so what we're going to see is that the determinant actually is related to dot product as well. So we're going to think about the dot product as a function. So here I have the the dot product of two vectors x and y. And what I mean by that is I take the vector x and I do a dot product with the vector y. And so this has this idea that it's linear in the first entry. So here I have a sum rule and a constant multiple rule in the first entry, and I have a sum rule and a constant multiple rule in the second entry. And just to give you an idea of how this would work, when I'm doing my dot product, I'm going to consider this as a summation and split it up. So here I'm thinking about this first term, x1 plus x2. I'm going to have a hard time keeping track of the notation, so I'm going to change the notation a little bit. Call it the vectors u plus v, and I'm going to do the dot product of u plus v with y. And a dot product means I take the entries of the first vector, so this is u plus v's entry, multiply by the entries of y, and I'm going to add those up. So if I add those up, there's this distributive property of multiplication and the linearity property of summation that allows me to split that product into two parts. So I have the dot product with u and y, and I have a dot product of v with y. And so I split. My dot product is linear. It allows me to split up sums in the first entry into two sums. And similarly, if I think about what's the dot product of a constant times a vector with another vector, I get to replace the entries of the vector cx, factor out the constant, and I get c times the dot product of x and y. Now at this point I need to give you a warning. A linearity means you do it either the first entry or the second entry. So if I'm going to do something like the dot product of the vector x1 and x2 and y1 plus y2, I don't get to split it up in a single step. I have to choose. So for example, if I split it first on that first term, I get the dot product of x1, but I can't split up the second term yet. So I get x1 dotted with y1 plus y2, and then I have the dot product of the second vector x2 with y1 plus y2. Now that I've split it, I get to split it again, and I can finally get, instead of two terms, there are actually four terms. I get the dot product of x1 with y1. I have the dot product of x1 with y2. I have the dot product of x2 with y1 and the dot product of x2 with y2. And mathematically, this is really, the dot products have a distributive property, x1 plus x2 dotted with y1 plus y2. Basically, what I did above is something akin to foiling, where, no, that last one was wrong, where I have 4 terms. And so that's how the dot product works. Is what we call bilinear, bi because there's 2 entries, and linear because each of the entries in the function are linear. Now the determinant can actually be viewed as a multilinear function, and here we're thinking of the determinant as a function of the rows of the matrix. You can think of it as the function of the columns as well. The tradition is that we think of it as rows, but everything I say about rows in the presentation are also true if I thought about it as columns. The arguments are identical. So, how do we calculate a determinant? Well, in this second paragraph, we remind you that determinants can be calculated as a cofactor expansion. And what I do is I take the entries of a given row, so here I'm thinking of the kth row, and I'm going to take each entry in the kth row, and I'm going to multiply it by a cofactor, and I'm going to add those up. And that means that my determinant is actually the sum of products, so it's a dot product. The determinant of A is a dot product of any row with the vector that comes from the cofactors associated with that row. Now, this means that everything that we know about dot products has some sort of interpretation for our determinants. So here's our first thing. We're linear in each term. That's what multilinear means. I have all of these entries, n inputs for the n rows, and I'm linear in each of those. Here's how I do it. I'm going to think about an arbitrary entry, an arbitrary row, and I'm going to think of it as a sum. And we need to show that the determinant has a sum rule for that particular entry. Well, this is a dot product of this kth row. And so this dot product, the vk is x plus y. Linearity lets me split that up into 2 parts. So we recognize that the determinant is a dot product of the kth row with the kth row cofactors. And now I split this into 2 parts. I have a dot product of the x vector with the cofactors. And I get to add that to the dot product of the other vector y with the same cofactors. So I have linearity. I have the sum rule at least. There's secondly the constant multiple rule, and here we're using the constant multiple rule of the dot product in the same way. So we're going to use this property throughout our argument. If we can write a single row as a sum of parts, we'll split it into 2 determinants. If I can see that a determinant has 1 row multiplied by something, I'm going to be able to factor that row out. Sorry, not factor the row, factor the constant multiple out. So the first key property of determinants that we want to prove is that if you exchange any 2 rows or any 2 columns, the determinant will change sign. There's nothing else that happens. And so in order to do this, we're going to start with the simplest case where adjacent rows are switched. So here I have my matrix A has the rows in order, and I have a new matrix, we'll call it B, and the only thing that's changed is the k and k plus 1 rows have switched order. So in the first matrix, we're going to imagine doing a cofactor expansion on the kth row, and on my new matrix, I'm going to do a cofactor expansion on what's now the k plus first row, but it happens to be the same vector as it was before. So I've written down the formula for the cofactor expansion. we're going to sum, so this is the dot product, we're going to sum along the elements of the row times the cofactors, where I have the sign of the cofactor times the determinant of the minor, where I take the row k and the column j out. So this is the determinant of my original matrix. Now if I think about the determinant of my new matrix expanding across its k plus first row, so I have the same vector elements, I'm going to have the same elements because I'm using the same numbers in the row, but when I calculate the cofactors I'm doing something a little different. I'm on the k plus first row, so I have a k plus 1 instead of k, and my determinant is for the k plus first row and the jth column. Now I put a little tilde over the top of my matrix for my minor, just to indicate that it's for a different matrix. But what I want to point out is if I cross out the kth row of the first matrix and the k plus first row of the second matrix, those are the same. And so these minors are all the same. So this minor, the two minors that I have in my calculation are the same. The only difference in the entire calculation is that there's an extra -1 power. So these determinants are equal to each other except for changing sign, because that extra power. Now that we know that if two adjacent rows are switched, the sign changes, we'll now deal with the case when the rows are separated by more than one apart. And we're going to do that by thinking about how many pairwise swaps we need to get to our final value. So imagine that I have some rows. Let's start with 3 rows, and I want to swap A with C. And I can only do that by switching things that are next to each other. So what would I do? I would switch first B and C, that pushes my C up. I can now switch C and A. And then I need to finish by putting the B down in the middle. And so we had 1 step, 2 steps, 3 steps. And if I thought about what that took, each pairwise swap would change by -1. So I have -1 cubed, which is -1. There were an odd number of swaps to finish that. So let's do this again. Let's do 4, A, B, C, D. And if I swap that, we're going to do the same sort of thing. We're going to bubble the D up to the top, A, D, B, C. And then we're going to bring the A down, A, B, C, D, B, A, C, and D, B, C, A. Okay, so we had pairwise swaps. We're just pushing this up and down. We had 1, 2, 3, 4, 5. It took 5 pairwise swaps to switch the first and the fourth rows. Well, in general, I'm always going to have this. If k minus L, let's put L in a squiggle, k minus L, that's my separation. And let's put it in absolute values because we don't know if k or L is on top. That's my separation. It's going to take k minus L to put the bottom all the way to the top. So I'm going to have k minus L to put it to the top, and then I have the same amount -1 to bring the other one down to the bottom. And so the number of steps is 2 absolute value of how far apart they are -1. And this is always odd. And -1 to an odd power is -1. So it doesn't matter how far apart two rows are. If you want to swap them, the determinant will always change sign by -1. Okay, we have our first row operation rule. If you swap two rows, it changes sign of the determinant. And there's a cool consequence of that. The consequence is that if you take the determinant of a matrix where two rows are the same, the determinant has to be 0. And here's why. If I have two rows that are the same, let's put them at the top just to keep it simple. The first and second rows are the same. Well, if you switch the order, it's the same matrix, so that it has the same determinant. But because you switched order, you also changed the sign. And so the only number that's equal to its opposite, so this number equals its opposite, let's do this in algebra, the determinant equals the opposite of the determinant. If I solve that in algebra, 2d equals 0, the determinant has to be 0. Ta-da! Any matrix with equal rows or equal columns, if any two rows or any two columns are the same, boom, the determinant 0. Well, the linearity property also gives us another one. One of our elementary row operations is to multiply a single row by a constant. So if I take the kth row and I change it by multiplying it by c, the multilinearity, if I take the constant multiple out of that one row, it gets multiplied by the determinant. So that's our second rule. Our second row operation. If we change a row by scaling it, the determinant scales the same way. And now we're ready for the third operation. This I find this is the most surprising for me. It says if you change a matrix by replacing a row, by adding to it a multiple of any other row, so it can't be the same, but multiply it by any other row, the determinant doesn't change at all. And that surprises me. Okay, so imagine here B's this matrix that we've changed row k to row k plus some constant times row I, and all that matters is it's a different row. So here's the determinant of our original matrix. It has our n rows, and I've just indicated the VI is just some arbitrary location in VK, and so this VK is the one we're going to change. Determinant of B, so B is the matrix that the kth row has been replaced by the kth row plus a constant times some other row. And we're going to use linearity on this single term. We're going to split this into two sums. So we split the where the kth row keeps the VK, and the other term, the kth row is going to keep CVI. Okay, this first entire determinant, well, that's our original determinant of A. So we have the determinant of A first. And the second determinant that we have has this constant multiple. We pull it out, so that's using our other rule. We pull it out, and now notice what we have. The k and ith rows are the same. And so the determinant there has to be 0. So the determinant of B and A are the same. And that's pretty cool. So here's an example of how I might use this property. So here I have a matrix. It's a 3 by 3 matrix, and I want to find its determinant. And if I think, what would I do to do row operations? Well, one thing I might do is I might say, well, let's change this first column, and let's put it in the first column in a row echelon form. So one thing I might do, I might want to put this -1 to the top. So let's do that. And now that I have row 1 and row 3 switched, maybe the next thing I want to do is change this sign so it's +1. And now that I've got a +1, I can use that 1 to eliminate the 2 and the -3. All right. So I have a new matrix now, and it's in this simpler form. Let's ask ourselves what happened to the determinant. So let's give these matrices some names. We started with A. Let's call this A after 1 step. This is A after 2 steps, and finally A after 3 steps. Technically 4, because that was 2 steps. Alright, so we have our matrices. Okay, well, what do we know? If I switch rows, I know that the determinant of A after 1 step is the opposite of the determinant of the original. Okay. Second, if I multiply a single row by a constant, that changes the value of the determinant by that same multiple. The determinant after 2 steps is -1 times the determinant after 1 step. And then I'm going to bring this down after 1 step, so we've changed sign twice. We're back to where we started. We have the same determinant as we started. Okay, what do we do next? Well, we do the third type of row operation, and that does not change the sign, or the determinant. So this has no change. And so the determinant of our matrix after 3 steps, in this example, is going to be the same as the determinant of our original matrix. And the advantage of this new matrix is I can do a nice convenient expansion along that first column. So we can say that this value, if I expand along this first column, is going to be 1 times the determinant I get with that little minor matrix, -8, 7, 15, and -10. And then everything else is 0, so plus negative, plus 0 times negative something, doesn't matter, plus 0 times positive something, doesn't matter. Those two cofactors we don't even need to look at. And so we get our value is 8 times 10 is 80, minus 7 times 15, 105, so our value is -25. If we were to go back to the original matrix and calculate the determinant, we get 3 positive terms. Well, let's expand across. How about we expand across the second row? So that cofactor, so we get not the matrix, the determinant of A is equal to the 2 times the cofactor, so that's the negative determinant of what I get if I get rid of the first column, 3, -4, and -4, 2. And then I'm going to add 0 times the second cofactor. So if I get rid of the middle column, -3, -4, and -1, 2. So that's the minor matrix. And I have a positive term for the cofactor. And our last number is 3 for the row. And we're now on a negative term for the cofactor. And what are the terms? We have -3, 3, -3, 3, and -1, 2. Alright, that's the cofactor expansion. So what do I have? I have 2 times 6 minus 16 is -10, change the sign to +10. Plus 0 times, doesn't matter, plus 3 times, what do we get? We get -6 minus -3, so that's -6 plus 3, -3, +3, 3 times 3, there's 9, so I get 20 plus 9, 29. Did I do something wrong? Yes, I did do something wrong. I'm looking, and that term I copied wrong. So that should have been a -4. Let's fix that. So that changes to a -4. And so this last term, -3 times -4 is 12. 12 plus 3 is 15. And I need to change that sign to -15. So I get 20 minus 45 is -25. Now, does that agree? Yes, okay. Phew! That's embarrassing when you make a mistake. But that illustrates how we can use our row operations in changing the determinant to allow us to calculate the determinant using row operations. And in class we'll go over that more, that particular step. So your goal is to understand the three rules and how they apply.